But before we begin to talk about the Z transform, I would like to refresh your memory about the Laplace transform. Okay. Now, Laplace transform is a transform that is applied in the continuous time. What other transform do we use in the continuous time? We use the Fourier transform. So, basically the Fourier transform and Laplace transform are continuous time transforms. So, for continuous time signals, there are two things that we use. One is the Fourier transform, and the second one is the Laplace transform. Okay. Now, you would have studied it in the context of signals and systems, but let me just refresh your memory. So, Laplace transform is done in terms of a variable S, which is equal to sigma plus j omega. Okay. So, S is a complex variable. Sigma is the real part of S, omega is the imaginary part of S, and omega is treated as a frequency. Okay, we will explain it in a moment why that is the case. Now, if you were to look at the domain that is covered by S, so this is sigma, this is j omega. So, basically the real part and the complex part. So, this is what we are looking at is the complex plane. And as as sigma goes from minus infinity to infinity, you cover the entire real axis. As omega goes from minus infinity to infinity, you cover the entire imaginary axis. So, S will cover the entire complex plane. S covers the entire complex plane. Okay. So, this is the, now let us look at the Laplace transform definition. The Laplace transform of a function x of t is given by x of s, which is minus infinity to infinity x of t e power minus st dt. Okay. Now, just for a moment, substitute for s, minus infinity to infinity x of t e power minus sigma t e power minus j omega t dt. Okay. Now, with this expression for x of s, are you able to see that the Fourier transform is a special case of the Laplace transform. So, we can if you set sigma equal to 0, then you will get the j omega axis going from top to bottom. As you go from minus infinity to infinity, this will give you the Fourier transform. So, the Laplace transform is the generalized transform, form. Okay. And the Fourier transform is a special case. Fourier transform is a special case of the Laplace transform, and that is a case where sigma equal to 0, set equal to 0. So, you get only the imaginary axis. Okay. And one more interesting result. Whenever we write down the Laplace transform, we also write down a region of convergence. Okay. So, we will typically say that sigma is greater than sigma naught or sigma less than sigma 1. It is given in terms of the real part, whether where the region of convergence lies. So, typically if you look at, there may be an example where for a function this could be the region of convergence. So, you have sigma naught here, the region of convergence is sigma greater than sigma naught. So, which means that the region of convergence is what is shaded in red. This is the region of convergence. Okay, typically this, and or you can have it on the left hand side, right hand side. Okay. Now, a very important element in this is if region of convergence includes the j omega axis. Okay, in this particular example, the j omega axis is included in the region of convergence. This means that the Fourier transform exists. Okay, because the Laplace transform exists for all these values of sigma naught, and sigma naught equal to 0 is a sigma equal to 0 is a special case, and it is, and since anyway it is part of the region of convergence, the Fourier transform will exist. Okay, so here is a summary of what we have said so far. We are very comfortable using the Fourier transform. Fourier transform happens to be a special case of the Laplace transform, and if the Laplace transform's region of convergence includes the j omega axis, which is the imaginary axis, then the Fourier transform will exist and we can apply either the Laplace transform or the Fourier transform. But the important thing to note is that even if the the Fourier transform does not exist, the Laplace transform may still exist, and therefore we can still use the transform techniques via the Laplace transform. Okay. So, that is a summary statement of what we already know about the transforms that we use for continuous time signals. Now, it is easy for us to explain the Z transform in the same manner. We can say that the Z transform is a generalization of the discrete time Fourier transform. Generalization of the discrete time Fourier transform. What do we mean by that? Look at the expression for the discrete time Fourier transform. X e of j omega is equal to summation n equal to minus infinity to infinity x of n e power minus j omega n. Now, if you were to look at the complex plane one more time, okay, where are we computing the discrete time Fourier transform? We are computing it on a circle whose radius is equal to 1. Why do I say that? E power j omega is a complex phasor whose amplitude is equal to 1. So, e power j different values of omega, this is the radius equal to 1, the circle with radius equal to 1, and you can think of omega as the angular frequency. So, that means I am not covering the entire z plane. So, this is the real part, this is the imaginary part. Now, if I want to cover the entire z plane, just like we did for the Laplace transform, that is what the z transform is doing. So, x of z, which is the z transform, is given by n equal to minus infinity to infinity x of n z power minus n, where z is equal to r e power j omega. So, z power minus n will be r power minus n e power minus j omega n. Okay. So, you can choose r less than 1, then you will get all points inside the circle. You choose r greater than 1, you will get points outside the unit circle. So, this is the region where r is less than 1. This is the region where r is greater than 1. And if you want all the points, you take r less than 1, equal to 1, greater than 1, you will get the entire complex plane. Just like you could get for the Laplace variable s, how do you get it? Omega going from minus infinity to infinity, and the j omega going from minus infinity to infinity. So, basically you have two linear variables that were going. Now, we are doing it in a different set of coordinates. Here we are giving it in terms of radius and angle. The radius can go from 0 to infinity, so you can cover all of it, and the angle goes from minus pi to pi or 0 to 2 pi. So basically, instead of two linear variables, we have the radius and the angle as the and that is what the Z transform is doing. Okay, so the discrete time Fourier transform is a special case of the Z transform. It is the transform that lies on the unit circle where the radius is equal to 1. Okay, so in other words, we can make the following statement that the Z transform is the discrete time counterpart of the Laplace transform. Discrete time counterpart of the Laplace transform. Okay. Just like the discrete time Fourier transform is a discrete time counterpart of the Fourier transform, you have the corresponding Z transform relationships also. Again, this is a very powerful transform because now you are saying I do not have to limit myself to the unit circle. I can look at the transform anywhere in the complex plane and we will be able to get the benefit of that. So, we can say that for the DTFT, we substitute Z equal to E of j omega. Okay. This means that you are looking at the radius being equal to 1 or mod Z equal to 1 or R equal to 1. Okay. The general form will be Z equal to R E of j omega, where R can go from 0 to infinity and omega will go from minus pi to pi or 0 to 2 pi. Okay. And you will see that the periodicity is obtained. Okay. So, here is the summary statement. So, the definition x of z is defined as like the DTFT going from n equal to minus infinity to infinity, x of n z power minus n. Z power minus n. This is the definition of that. Okay. We can simplify it by substituting z equal to r e power j omega and get the following expression. This is equal to summation n equal to minus infinity to infinity x of n r power minus n e power minus j omega n, and if I put a bracket around this, it looks like the DTFT again. So, the Z transform of x of n is also identically equal to the discrete time Fourier transform of the following sequence x of n r power minus n. Okay. So, basically it is an exponentially weighted sequence for which we are computing the discrete time Fourier transform. So, in other words, and we can say that the r is a real number. So, r is an element of the real number set basically and r is positive, non-negative. So, r greater than or equal to 0. Okay. So, this is the condition that is satisfied. So, r is a real number which is greater than or equal to 0, and we look at an exponential weighting of the sequence, and so this is how we write that. So, how do we denote the Z transform? We say x of n has got a Z transform, just like we wrote f for the discrete time Fourier transform. This will give us an x of z. Okay. And just like all other transforms, we will also define a inverse Z transform. Inverse Z transform that will bring us back to the original sequence. All right. So, here is the application of what we already know from discrete time Fourier transform. Okay. Now, we said that the Z transform is identically equal to the discrete time Fourier transform of, so Z transform of x of n. Z transform of x of n and equal to discrete time Fourier transform of x of n r power minus n. Okay, we said that this was the the condition. We already know the condition for the existence of the discrete time Fourier transform. Condition for the existence, which is another way of saying I want to know what is the condition for uniform convergence. Okay, not mean square convergence, this is uniform convergence. Okay, uniform convergence. The condition for uniform convergence is that absolute summability criterion, right. So, the sequence must be absolutely summable, absolutely summable. Okay. And absolute summability condition basically says summation summation n equal to minus infinity to infinity x of n r power minus n modulus, this must be less than infinity. Okay. So, what is the region of convergence? The region of convergence is identically equal to the range of values of R, range of values of the radial function, radial variable, for which x of n r power minus n is absolutely summable. Okay, the ROC of the Z transform is the range in which the we have related it to the discrete time Fourier transform, and we know the condition for uniform convergence of the and we say that this is the expression where the sequence x of n r of minus n is absolutely summable. Okay, let me give you a minute to sort of put all of the pieces in place. The Z transform, we started out by looking at the Laplace transform, how the Laplace transform is a generalization of the Fourier transform. The Fourier transform as a special case of the Laplace transform. The Laplace transform variable covers the entire complex plane. In the same manner, we have found a way by which we can cover the entire complex plane, not as the real part and imaginary part, but in terms of radius and angle. Radius goes from 0 to infinity, angle goes from minus pi to pi or from 0 to 2 pi, and that is how we have defined the variable for the Z transform. We defined the Z transform and then said that it is the same condition as a discrete time Fourier transform of x of n r power minus n. We used the condition for the uniform convergence of the discrete time Fourier transform and said that using the same criterion we can now get the region of convergence of the Z transform. Okay. So, one of the important things to note is that the region of convergence depends on the value of R. Okay. Once you know that it is convergent for a value of R, the value of omega, which is between 0 and 2 pi, that really does not matter, because you are always looking at it in terms of a modulus of the value. So, therefore, if the region of convergence depends on the value of R. So, we can also make a statement that if the Z transform exists for one value of R, for one value of R, okay, with R with some angle, okay, let us say that this can be written as Z equal to R e power j omega naught, some omega naught it exists, then the Z transform will exist. Okay, Z transform exists for all points on that circle with that radius r. For all points on the circle with radius equal to r. Okay, it does not depend on the angle, it depends only on the radius. Okay, now is there a similar situation with the Laplace transform? Actually, there is. Remember, when we specify the region of convergence of the Laplace transform, we just specify it in terms of the real part. We never specify it in terms of the imaginary part, because once you know that it converges for a value of sigma, it will converge for all values of omega minus infinity to infinity. So, the important thing to note is that just like you did it for Laplace transform, there it was in terms of the real part of the Laplace variable s. Here we are writing it in terms of the radial function that we have defined in terms of z. Okay. So, one thing to note is that the ROC, whenever it is specified, it will be specified in terms of the value of r. Okay. So, if you were to look at the definition of the ROC, here is something that we would encounter. Okay. So, you have a circle. Let us say the circle has got a radius r1. Okay. The ROC could be mod z greater than r1 or mod z less than r1. You can see that two options are possible. Now, you can also see that there could be one more condition, that supposing there was a second circle with radius r equal to r2. Let us say this was equal to r2. So, now you can see a region of convergence which could be in the following manner: mod z greater than r2 or mod z less than r1 or mod z greater than r1 less than r2. Okay. So, it could be outside of the outer circle, it could be inside of the inner circle, and or in between the two circles. Now, what decides the region of convergence? I think that is a very important question. What decides the region of convergence is a very simple condition, that the region of convergence cannot include any poles. Include any poles. Okay, what is a pole? When you write a transfer function in terms of a numerator and denominator, let us just take a minute to do that. Supposing we were to write down a polynomial, okay, p of x divided by q of x. This is a rational transfer function. Then the zeros, this is, let us say, h of x. Okay, x is just as a general variable. Zeros of p of x. Okay, that means the polynomial p, if you substitute these values away, the polynomial will go to 0. These are the same as the zeros of h of x. By the same token, zeros of q of x. Okay, that means q of x will go to 0. It is in the denominator. So, that means h of x will go to infinity. So, the zeros of q of x are the same as the poles of h of x. The poles essentially stand for those values of x for which the function will go to infinity. Okay, the value of the function goes to infinity, that is pole. What is a 0? The value of the function goes to 0. So, the difference between a pole and a 0 is that at a 0 the function goes to 0, at a pole the function goes to infinity. So, what we are saying is the region of convergence cannot include any pole, it has to exclude the poles, because we want the Z transform to exist. That means it has to have some uniform convergence. It cannot be something that just goes off to infinity, right? So that is why we have imposed the condition that we are looking at the ROC. The ROC is specified in terms of the radius r, and it should be a region where none of the poles are included.